Section is Lagrange Multipliers.
Lagrange?
It is a French name, yes.
Lagrange?
No, it is not Lagrange.
That's what Coop calls it, but it's not.
What is it? How do you say it?
Lagrange. Yes. Anyway, what we're going to do is actually revisit a problem that we did yesterday. Yes. We were interested in minimizing the surface area. And we found that the surface area equation was going to be xy plus 2xz plus 2yz. And the constraint was that the volume, which was found by taking the dimensions x, y, and z, multiplying them, had to be 32.
So it was the cube.
This is the cube, yeah, the box with no lid. What was the minimum surface area? Okay. So now what we did before we just solved for z, plugged it into S, and minimized. So once we isolated z, we had a function in two variables, and we did the first partials, and so on and so forth. And everybody was happy. Well, what if that doesn't work? Maybe you can't plug in z or isolate it easily or get just a function of two variables. Maybe it's a function of three variables, in which case finding the max and min actually is possible, but it's much more complicated than the stuff we've been doing. So what we're going to talk about is the method of Lagrange multipliers. Here's the idea. Probably the easiest way to explain how these work is to start with a scenario to kind of illustrate what is going on. So let's say we have a rectangle. So suppose we want to find a rectangle with the largest area inscribed in the ellipse x squared over 9 plus y squared over 16 equals 1. Let's see. So, picture. So we see what's going on. X-intercepts are 3 and negative 3. Y-intercepts are 4, negative 4. So here's our ellipse. And now what we're trying to do... How do I do what?
You do that so well. I try to draw a circle and it looks like a square.
I can draw pretty circles too on the chalkboard.
Yes.
Can you freehand circles? Can you freehand circles?
Yeah. So what we're looking for is this. We're trying to find a rectangle that we can inscribe in the ellipse so that the area needs to be a max. Okay. So the constraint is actually this function here. I'm going to just call that g of xy equals x squared over 9 plus y squared over 16. There's our multivariable function. Now, obviously, we're interested in specifically the one that's equal to 1, but just bear with me for a second. So here's our constraint. And then the function that we want to be maximizing is area. So we have to come up with a system to identify the area of this blue rectangle. So let's say that this is located at x comma y. Then what would the area for the rectangle be? 2x times 2y, which is 4xy. Very good.
How do you figure that?
Because if this is x, then from here to the center is x, to the center the rest of the length is 2x. So the length is 2x, and then the width would be 2y. Okay? So here's what we're going to do. We're going to consider g of xy as a set of level curves in particular, we'll be interested in the one that's equal to 1, since we already know that. And we'll also do the same with, let's call it f of xy equals 4xy. Okay? So essentially what we have, if I redraw the picture, is the one particular level curve, which is the one we already graphed. So this is the level curve for g of xy equal to 1. And now we don't really have any particular level curves for 4xy. So if we set 4xy equal to some constants, if I isolate y, we get that y is going to equal k over 4x. Which is essentially just another constant over x. So this is just a set of hyperbolas, right? Similar to the function y equals 1 over x, just a little different because the constant's different in the numerator. You can certainly play around with this constant, make it equal to 4, make it equal to 1, make it equal to anything you want. And what happens then is now you get a set of level curves which of the three, and I kind of drew a bad set in the third quadrant, but which of the three curves do you think are the ones that we're going to be interested in? Because these are the ones that are barely or just touching that constraint. Does that make sense? Okay. So now, let's write this down. We are interested in the level curve that barely satisfies the constraint. In other words, tangent to the ellipse in this case. What we know then is that two curves are tangent at a point if and only if their gradient vectors are, well, let's look at it. If we have two curves, what do we know about gradient vectors? They're normal to each curve. So maybe the normal vector for the curve on the right looks something like that. This, let's say this is the gradient of f. And then this gradient might look something like this. That would be the gradient of g. What do we know about these two gradients? They're parallel. I mean, they may be opposite, they may not, but they have to be parallel. So that means that the gradient of f of xy, how do we know if vectors are parallel again? Scalar multiples, right? So now here's where the name comes from. We use a constant called the Lagrange multiplier,
Oh my god.
which is lambda, yes.
What?
What?
It's a Greek letter.
Don't you see it? It represents something.
Liam,
Fine. Make it, think of a negative.
Anyway, this is one gradient. This is another gradient. We said they have to be scalar multiples of another. This is called the scalar, but in particular it's the Lagrange multiplier. And now, this is really the method right here. So if you identify the constraint and you identify what the function is that you're maximizing or minimizing, you set up this system of equations here, and then you solve. So solving the system of equations that result from this is called the method of Lagrange multipliers. Okay, so that's the background for the new method that we're going to introduce to solve, again, the problem from yesterday with the box, minimizing the surface area. And then we'll do one more example, and that's it. Okay. Any questions so far? All right, so let's revisit again. So let's solve yesterday's problem using this method of Lagrange multipliers. So we had f of xy equal to 4xy.
Wait, we never solved the one from before.
That's the same one.
No, but the one with the rectangle with like area and the ellipse.
This.
Oh, I didn't. You know what? What was I talking about? I don't want to solve the one from yesterday yet. That's later. Let's not solve yesterday's problem. You're right, Eddie. We'll solve that in a minute. That's the last example. Let's solve the one that we were talking about. That's what I meant to say.
Yeah.
Sorry, long night last night. Those math meets will get to you.
Yeah.
So we have 4xy, and it was subject to a constraint of x squared over 9 plus y squared over 16 equals 1. And we call this g of xy. Okay? So let's find the gradients for each. Gradient of f would be what vector? 4y, 4x. The gradient for g, our constraint function,
Uh, 296.
296, and
1/4 x.
Yeah,
Y.
Yeah.
I'm hearing like 3 different answers.
1/8. No, it's 1/8.
It's just y over 8, isn't it?
Yeah.
Okay. 2y over 16, 2/16 is an 8. So now, since the gradient of f has to equal the Lagrange multiplier times the gradient of g, then we have that 4y. So I'm just taking component by component. The x component here has to equal the x component here just with a lambda in front. Does that make sense? So 4y has to equal I'll put the lambda in front of the x. 2 lambda x over 9. And 4x has to equal what? Lambda y over 8. Okay? So now, the main idea here...
It's that homework problem.
What's that?
It's kind of like that one homework problem.
Oh, which one?
Well, the one where you have to find like a gradient parallel to something else.
How about the heat-seeking particle problem?
Except you use k instead of line.
It's pretty similar. So, first I'm going to say we should get lambda alone. So, if I solve for lambda, let's use the first equation. What do we get? Okay. Second, so here I solved for lambda. Now I'm going to substitute into the other equation. So we get 4x has to equal, what would that be? 18y squared over 8x. We can reduce that. Divide by 2.
Plus u.
And if I multiply by 4x on both sides, I get 16x squared has to equal 9y squared. So essentially what I'm doing now is trying to find a relationship between y and x. Once I have a relationship between y and x, I can then use the constraint equation to figure out what those have to be. So let's get x squared alone. X squared will be 9y squared over 16. So now the idea is that you can now...
You're not going to square root that?
Well, I could, but look at the constraint. Where's the constraint? Right here. Since x is squared anyway. So using x squared over 9 plus y squared over 16 equals 1. I'll just go ahead and replace x squared now. So that becomes y squared over 16 plus y squared over 16 equals 1. So y squared over 8 has to equal 1. So y has coordinates of plus or minus 2 root 2.
Did you plug that into the function rather than the constraint?
Well, if we plug it into the function, what are we setting it equal to? You see what I'm saying? Like if I plugged it in here, then I wouldn't be able to solve because I don't know what that equals. Whereas the constraint, I know the constraint has to give us 1. So that makes more sense to plug it in there. All right, so we're trying to find max area, although technically it's not going to matter because those are just the coordinates of the points. But let's go now figure out x. Let's see, x squared from right here is 9y squared over 16. So I'm going to plug in 2 root 2 and square that to multiply it by 9. So 9 times 8 is 72. So then x squared, you can, let's see, divide by 8, so 9 halves. So then x would be plus or minus 3 over root 2. Okay? So looking back at our original scenario, these are the coordinates of the 4 points. Do you guys see that? So we have x will be 3 over root 2, 2 root 2, and then just mix them all up to get the 4 locations. But now the problem was to find the max area, right? So how do we find it? Distance.
Why?
Can't we just plug it in? Because we know the area has to be 4 times x times y. So the area would be 4 times 3 over root 2, and then y was 2 root 2. So the max area here is 24 units squared. Okay. Any questions on that example? There's going to be some times where you have to be careful with scenarios where x could be 0. Like, for example, let's go back here for a second. Right here. We're going to say that x and y cannot equal 0. I mean, technically, if you look at this system of equations here, do you see how x and y both could be 0, and that would solve these two equations here? Because if x is 0 and y is 0, 0 equals 0. Okay? Now, what you have to look out for is maybe, what if x is 0? Can y be something else?
No.
So if x is 0, what does y have to be? Y has to be 0. So if x equals 0, y has to be 0. This is impossible because why?
The area is 0.
Then the area is 0. Does that make sense? So occasionally you have to look out for those values. For example, if I got x is 0, but then I could get a value for y and you plug it in and it actually gives you a value that makes sense, that would be considered another max or min, possibly. Okay? In this case, we don't worry about it though because it doesn't make sense to have either of these equal to 0. Okay? All right. Last example. Now we'll talk about the example from yesterday. Sorry. We had s equal xy plus 2xz plus 2yz and it was subject to the product xyz equal to 32, and we're looking to minimize this function here. Okay, so using the method of Lagrange multipliers, I say that f of xyz will be my surface area equation. G is the constraint, so that will just be xyz. Now I'll go ahead and find the gradients of each. So gradient of f would be what?
Y plus 2z x plus 2z 2x plus 2i.
Good. And let's go ahead. I'll just write lambda gradient g, since that's what we need anyway. So the gradient of g, put a lambda in front of each component, we get lambda times yz, and then lambda times xz, and then lambda times xy. So here's our system. We get y plus 2z has to equal lambda yz. X plus 2z has to equal lambda xz. And then 2x plus 2y has to equal lambda xy. So we can probably do the same kind of thing, and it's going to look a little different. So we'll see what to do when we reach that bridge. Let's isolate lambda. So lambda from this equation would be what? Yes, I'm going to write it in like system format. So like what plus what? 1 over z plus 2 over y, right? And then lambda here will be, again, 1 over z, but now plus 2 over x. And then here it's 2 over y plus 2 over x. Okay. So the goal here, once we have this, we want to find a relationship for maybe for y in terms of x. Because we want to reduce this to one variable so I can actually solve, get x equals whatever and then plug it in. And we want to do the same with z. We want to use the same variable. So somehow I want to use these equations to get a function for y and then a function for z.
1 over z equals 2 over y. Is that what you do?
1 over z
Equals 2 over y.
equals 2 over y, does it? How'd you get that?
Well, because if 1 over z plus 2 over x equals 9, then so is 2 over y plus 2 over x, then 1 over z has to equal 2 over y.
Yes. But, okay, that's true. But if you decided to make z in terms of y, then you'd have to also make x in terms of y. And you can do that. It's going to be the same stuff. Just to keep things consistent, I'm going to try to get things in terms of x. But you're right. So right here I see from the first two equations, do you guys see that if I subtract the two equations, what do we get? Or, you can just look at it, I think, right? What do we know about these two terms here?
3.
They have to be equal, right? And that's kind of what you were arguing, just
Yeah.
with y. So I'm going to say that 2 over y has to equal 2 over x. So then now y would be x. So now I know what y is in terms of x, right? And now let's see if I can find a relationship between z and x.
You just look at 1 over z equals 2. She said
1 over z
Equals 2 over x.
equals 2 over x. So then what's z? 1/2 x, right? So here are the two variables, which now I have in terms of just 1. So if I go back, what did we do once we knew what each variable was equal to? Plugged it into what? Yeah, the constraint. So the constraint was x, y, z has to equal 32. Well, now we know that x is good, y is also x, z is half x. This is now going to be 1/2 x cubed equals 32, so x cubed is 64, so x has to be 4. If x is 4, y is 4. If x is 4, z is 2, and these are the same dimensions we got yesterday, right? Okay, so that's kind of the idea behind Lagrange multipliers. Again, here's another scenario where having x, y, or z equal to 0 doesn't make sense because, look at the constraint, right? So you do have to look out for that. So if you're doing the homework and you're like, what? Where are they getting this weird minimum from that I missed? That might be where. Okay? So just look out for that, and we'll go over some of that on Monday. All right, as far as homework questions